Welcome to Echoes of Oddbo, the podcast exploring the strange, the mysterious, and the curious. Let's dive in. Have you ever wondered why the Earth, weighing about 6 times 10 to the power of 24 kilograms, or 60 sextillion tons, can seemingly hover in the vast expanse of space without falling like an apple? At first glance, this question seems simple, but it touches on some of the deepest aspects of gravity, spacetime, and the cosmic order. In fact, this question has repeatedly appeared in the comment sections of popular science videos over 500 times, not only reflecting public curiosity but also serving as a gateway to the core ideas of modern physics. 1. The Earth is actually always falling. First, let's dispel a common misconception. The Earth is not floating motionlessly in space. On the contrary, it revolves around the Sun at a speed of about 30 kilometers per second while simultaneously rotating on its axis. Here's the astonishing fact. The Earth is indeed falling, but it will never land anywhere. This may sound paradoxical, but it is precisely the truth revealed by Newtonian mechanics and Einstein's general relativity. Under the Sun's strong gravitational pull, the Earth should fall toward the Sun's center. However, because the Earth possesses a huge tangential velocity, its orbital speed, it continually misses the Sun as it falls. Physicists call this motion a free-fall orbit. Imagine standing atop a tall tower and throwing a stone horizontally. It will follow a parabolic trajectory and land at a certain distance. If you throw it faster, it travels farther. If it reaches the first cosmic velocity about 7.9 kilometers per second, it no longer lands. It orbits the Earth in a circle. The stone is still falling, but the Earth's surface curves away at the same rate, creating a stable orbit. The Earth's revolution around the Sun works on exactly the same principle, just on a scale billions of times larger. 2. The delicate balance of gravity and inertia. So why doesn't the Earth get pulled into the Sun? The answer lies in the dynamic balance between gravity and inertia, or centrifugal effect. The Sun's gravity, as the Sun accounts for 99.86% of the Solar System's mass, its gravitational pull holds the 8 planets firmly in orbit. The Earth's inertia, according to Newton's first law, the Earth tends to move in a straight line at constant speed. Gravity bends this straight path into an elliptical orbit. These two forces do not oppose each other, they work together to create a stable Keplerian orbit. In simple terms, the Sun pulls, the Earth rushes forward. This tug-of-war maintains a near-perfect elliptical path. This balance is extremely sensitive. Calculations show, if the Earth's orbital speed decreased by roughly 10%, its orbit would shrink dramatically, and it would eventually plunge into the Sun. If its speed increased by about 40%, the Earth would escape the Sun's pull and become a rogue planet drifting through interstellar space. In reality, the Earth's speed is just right. Just right. That is no coincidence but the result of billions of years of solar system evolution. 3. The mathematical code of planetary orbits, the Titius-Bode law. Even more astonishing is that the arrangement of planets in the solar system seems to follow a hidden mathematical rule. In the 18th century, German astronomers Johann Daniel Titius and Johann Elert Bode proposed an empirical formula, later known as the Titius-Bode law, A equals 0.4 plus 0.3 times 2 to the power of n, in O. Where n is an integer sequence, Mercury n equals minus infinity, Venus n equals 0, Earth n equals 1, Mars n equals 2. This formula remarkably predicted the orbital radii of known planets at the time and successfully predicted the existence of the asteroid belt, where Ceres resides. Although modern celestial mechanics views this law not as a fundamental physical principle but as a byproduct of orbital resonances and protoplanetary disk dynamics, it still hints that the solar system is not randomly arranged but governed by deeper physical rules. 4. The nature of gravity, curved spacetime. Back on Earth, what generates the gravity we feel, and why don't we float away? Traditionally, gravity was seen as a force, pulling downward. But in 1915, Einstein's general relativity radically transformed this understanding. He proposed that gravity is not a force but the manifestation of mass-curving spacetime. The Sun's enormous mass warps the surrounding spacetime, like a bowling ball on a stretched rubber sheet. The Earth doesn't get pulled, but moves along the straightest path, called a geodesic, in this curved spacetime. Our sense of weight comes from the Earth's surface, preventing us from following this curved path freely, producing a reactive force. Thus, the Earth's orbit around the Sun is not due to a literal pull, but because it rolls naturally along curved spacetime. In the universe, there is no absolute up or down motion is determined by geometry. 5. Life's cradle. The coincidence of multiple factors. The Earth's orbit is not only stable but its environment exhibits astonishing habitability. Perfect Earth-Sun distance. Within the Sun's habitable zone, allowing liquid water. Appropriate rotation period. 24-hour day-night cycle prevents extreme temperature swings. Moon's stabilizing effect. The Moon's mass and distance stabilize Earth's axial tilt, approximately 23.5 degrees, ensuring long-term climate stability. Magnetic field protection. The liquid outer core generates a magnetosphere that shields the atmosphere from solar wind. Jupiter is a cosmic cleaner. Its gravity removes many potentially hazardous small bodies from the solar system. Even a slight change in any of these factors, larger solar mass, slower Earth rotation, closer or more distant Moon, could prevent life from arising or evolving. 6. Was the universe designed? Given such precise balances, some wonder, is all this mere chance, or is there some design or algorithm behind it? Mainstream science suggests that it is natural selection on a cosmic scale. Countless star systems form and perish, but only systems with just right parameters, like the solar system, can host life capable of asking these questions. This is the anthropic principle. We observe a life-permitting universe because only such a universe can produce observers. Yet from the fractal distribution of galaxies, to symmetries in quantum fluctuations, to the precise values of fundamental constants like the fine structure constant, the universe reveals profound mathematical harmony. As physicist Eugene Wigner said, the unreasonable effectiveness of mathematics in the natural sciences is a miracle. We are the universe becoming self-aware. Next time you gaze at the night sky and see that blue planet quietly suspended in darkness, remember, it is not motionless but hurtling at 30 kilometers per second through curved spacetime. It does not exist by mere luck but is the product of countless physical laws, initial conditions, and evolutionary paths cooperating over billions of years. The Earth's hovering is not the end of a miracle, it is a microcosm of cosmic order. And we, the conscious beings on this planet, may be the universe's way of understanding itself. As Carl Sagan put it, we are made of star stuff. Now we have the power to think about the stars. In the vast expanse of space, the Earth does more than float. It tells a grand story of gravity, geometry, time, and life. And you and I are part of that story. Thanks for listening to Oddbo. Stay curious, and see you next time.